we go. The audio is working because you can see the mic level is fluctuating. So that's all good. This is the previously part, of what we talked about on Tuesday. So on Tuesday, we were working on the carry look ahead mechanism, where we basically want to reduce or eliminate the dependency of ki on ki minus 1, and then ki minus 1 depends on ki minus 2, and so on. So that's kind of where we left off. Okay, I kind of talked about the big, gigantic, ugly, expression, at the bottom. But what we'll do today is kind of roll back a little bit. We start with the conclusion of the long proof, and then we'll start from there. So it's 9 o'clock right now, so we can actually start today's lecture. So that's really just kind of like a previously in those TV series, just to kind of bring you up to date of the context of today's lecture. All right, so we don't need this YouTube thing anymore, so we can keep it here, but we don't need to play it anymore. All right, so we are still on the topic of adding binary numbers, and I regenerate the HTML version, or so I thought. Refresh, there we go. Yeah, so I did regenerate it. I didn't really change any content. I think I fixed one typo. I mistyped the NAND as NADN. Okay, I transposed the last two characters, but caught it, fixed it. Okay, but the newer version has a table of contents at the very beginning of the page, so that makes it a little bit easier for you guys to kind of navigate to a particular section. So what we'll do today is to navigate straight to section 6, because that's the beginning of the discussion of carry look ahead mechanism. So I'm not going to repeat the proof here. Okay, so what is important is we just have to say that ki plus 1 in subscript is basically the same thing as when you expand out everything. It is now expanded to xi and yi, or, and then in parentheses, xi or yi and ki. So remember, when we look at Boolean expressions, sometimes I borrow the same operators from arithmetics. Okay, so multiplication is basically conjunction, addition is disjunction, and then if I do need negation, it's an exclamation point. So is that okay so far? Notation-wise. I'm not going to go through the derivation. We talked about that on Tuesday. So what we'll do today is to move on from here. Okay? So what we'll do is we're going to say we'll define, okay, g of I to be xi, yi. We'll define pi to be xi or yi. So one is the conjunction of the x and the y terms. The other one is the disjunction of the x and the y terms. So don't ask me why we call it P and G. Okay, well, there's a reason, but I'm not going to talk about that. But this is just by definition. So by definition, GI and PI are defined right here. Are we okay so far? So you might notice that the expression that we had earlier for ki plus 1, the first term is really just GI. Now that we have an abbreviation GI, we can just substitute it. The second term, to conjunction with ki, is really just pi. So now we can rewrite ki plus 1 as gi or pi and ki. Are we okay so far? We're just changing the notation a little bit. Instead of writing out the long format, we are now saying, oh, we can shrink it because we can now define gi and pi like this. Then we can simplify the equation to just, ki plus 1 is gi or pi and ki. Are we okay so far? Okay. But the problem still remains. The problem of a carry depending on the carry immediately before that is still here, because ki plus 1 still relies on ki. Okay, so we'll go ahead and see. Okay, how can we get rid of this particular dependency? And we'll work with K1 first. So plugging in I equals to 0, okay? If I plug in I equals to 0, I plus 1 becomes 1, right? And gi is g0, pi is p0, and ki is k0. Okay, well, that's a quick and easy substitution. So with that, we end up with k1, k1 is g0 or p0 and k0. Okay, no big surprises there, right? Because all I did was to substitute the I with a 0. And this one is okay, even though k1 does depend on k0, it's fine. Because k0 is one of the input pins. You can't, it's not computed from something else. So this is fine, not a problem. So now we work with k2. So and when you substitute I equals to 1 in this equation here, when I equals to 1, then we get this. We get k2 equals to g1 or p1 and k1. Okay, no big surprise there. But we don't like the reference to k1 because the reference to k1 means, oh, until k1 is done, I can't really work with this expression to come up with k2. That's a problem. So, but now that I know how k1 can expand to other terms, we just do a substitution. So we plug in the term or the expression of k1 in place of k1 like this, and then we use distribution, and then we end up with an equation or an expression that does not depend on k1 because k1 is now substituted by an expression that only involves k0. But what about all of those other terms? I mean, this looks simpler, this looks more complicated. Is it really better? Well, okay, so you have to think about the level of gates that we need to deal with. In other words, if I give you the ability or the freedom to use logic gates of any number of inputs, okay, because normally, up to this point, we only use logic gates that have 2 inputs, right? The AND gate only has 2 inputs. But you can have AND gates of any number of inputs. Like in this case, I can have an AND gate that has 3 inputs. One input would deal with P1, another input would deal with P0, and then another input would deal with K0. That's one level of gate logic. Is that okay? But then someone's going to say, what about P1 and P0? Those are not input pins. Well, they're not input pins, but they are pretty close to input pins because all the P terms only rely on the disjunction of the corresponding X and Y terms. That is why I want you guys to understand how to use a multi-bit gate, because instead of splitting the input pins into a magnitude of wires and a whole bunch of gates, you can just do it with like 2 wires going in, and then you have all the P terms and all the G terms done. All right. So do we have any questions at this point? Okay, so let's analyze these circuits for now and try to figure out how many levels of gates do we need to do the computation. We'll start with K1. And if you have any questions about the analysis, please stop and ask questions. All right, so we'll start with K1. I'm just going to repeat the equation here. K1 is G0 plus P0, K0. Okay, so at the very first level, the values that are not computed, those are just input pins. Those are the X, the Y, and K0. Those are the input pins. Those do not require any computation. So what we do is now we say the first level of logic is going to say G0 is X0, Y0, the conjunction of those two. At the same time, in parallel, we can also compute P0 as X0 or Y0. These two can occur at the same time by 2 different gates. Are we okay with that? Okay. So now we get these 2 terms. Now with these 2 terms, we can start to compute. We also need the conjunction of P0 and K0. Okay, that's fine. We can do that. So the next level of gate is going to say, oh, we'll compute the P0, K0. So I'll number these things as level 1, the lowest level. This is level 2, the next level. And once we have P0, K0, then we can finally compute, we can deal with the outermost or the highest level disjunction operator. So now we can compute G0 plus P0, K0. This is level 3. All right. So that means we need 3 levels of gates in order to compute K1. Starting from just input pins, we'll need 3 levels of gates in order to compute K1. Okay, so now we'll go ahead and do another analysis. And this time the analysis is for K2. So what do we need to compute K2? Well, we have a whole bunch of G and P terms this time. Okay, fine. So we'll say, we'll compute G. We do need G0, okay? So X0, Y0, that's level 1. And then we need G1. Now G1 and G0 can be computed at exactly the same time. In fact, once you know how to use a multi-bit gate, they can be done by the same gate in Logisim, and that's why we had that exercise on Tuesday. Is that okay? Cool. And what about the P terms? Well, we need P0 and P1, so let's get those things done. P0 is X0 or Y0. P1 is X1 or Y1. And all of these can be done at the same time. Are we buying that? There's no interdependency between the G and the P terms. Cool. So level 1 is doing that. Level 2 is to say, we'll compute the conjunction here, the conjunction here. So that's what level 2 needs to do. So now we'll say, here's level 2. Level 2 is going to compute P1, G0. It's also going to compute P1, P0, K0. And those can be done at the same time because there's no interdependency between these. Are we good so far? And what are we going to do as the very last step? The disjunction, the overall disjunction is the very last step. So level 3 is responsible for the disjunction. So now at level 3, it's just the entire equation. G1 is coming from level 1, but we can't really do anything else with G1 until we get to level 3. And then we have a P1, G0. And then we have P1, P0, K0. Oh, so with 3 levels of gates, I can get K2 computed. Isn't that the same number of levels as K1? So even though K2, when you look at the expression, it looks more complicated. If you think about the number of gates it needs to compute the result, it's still the same. That is really cool because without this mechanism, it would have a linear relationship. It needs to rely on the previous carry and then the previous carry, so the amount of time to compute the carries would not be the same. Okay, so if that is the case, we'll take a look at K3 then. K3 is even more crazy, right? Because K3, by using our expansion, is G2 or P2 and K2. So it depends on K2. But guess what? We are not going to say, until K2 is computed, we won't start with K3. We're going to say, let's expand K2 in place. We know what K2 is. K2 is this expression. So we'll take that expression, expand K2 right into that expression here. And therefore, we remove that dependency. Is that okay? Are we? Yep. K0 is the input carry.
Right, but we're assuming it's not going to be 1.
We don't know what it is. That's why it's an input pin. So it is specified by whoever is specifying the value of the input. Just like the X bits and the Y bits. Okay. But once we expand it, we can now distribute just like before. So now we end up with something that's a little bit longer, right? So I'm not going to tell you, I'm not going to enumerate, what the levels are. Level 1 is always what? Computing the p's and the g terms, right? So we got one more term to compute this time, two more terms. We got g2 and p2 to compute. But remember, we can do all of the p and the g terms, together, in one single level of gates because there's no interdependency. Second level of gate. Let's get this conjunction done, and this conjunction done, and this conjunction done, and they can all get done at the same time because there's no dependency between these three. And then level 3 will take the results from level 2, and also one thing from level 1, and then that's our final or last disjunction gate. Is that okay? So once again, how many levels of gates do we need to compute K3? 3 levels. Cool. Well, what about K64 with a 64-bit adder? What do you think is the number of gates that we need, assuming we can have an arbitrary number of input pins for our gates? 3 levels. So it doesn't take any more time to compute K64 compared to K1. Now that is cool. That is the power or the reason why we have carry log ahead adder as opposed to carry propagation adders. Are we good so far? Yep.
So K64 will still depend on P1 and P0. Is that correct?
Yeah.
Okay, but won't that add to the processing time of the processor?
No, because
So we will get rid of that K63, K62, but will we still have a lot of stuff to add and compute?
well, I can kind of tell you how ugly K64 is going to look like. So K64, if you look at this pattern, is going to be G63, right, plus P63, G62, plus, and then a whole bunch of stuff, right? The last term is going to be particularly ugly because it will have P0 all the way up to P63 and then K0. But nonetheless, it is still only 3 levels of operators. Okay, so now the next thing we need to talk about is, okay, now I'm looking at an expression, a Boolean expression. How do we translate a Boolean expression into the structure of gates that we need to do the calculations? Open and close? Well, I'm not exactly sure what you mean by open and close.
So if you want to translate booleans into gates, we can have the circuit as open or closed. Is that what you mean?
No, I'm more thinking about, I'm looking at this and I'm asking the question of how do we, in LogicSim, how do we actually come up with the gates to do exactly the same thing as the expression? Okay. Sorry? Go ahead. I think you got the answer. Go ahead. With AND gates and OR gates, right? So we got one AND gate here, one AND gate here, one AND gate here, and then whatever the output of these AND gates are, plus the G2, they all go into one OR gate, right? And then the G0 and the G's and the P terms, have their own little gates to compute, those results from the X and the Y's. Okay? But I want to give you a kind of more systematic way of converting an expression into the structure of gates because that can be helpful, right? Okay. So what we'll do next is a little bit of diversion. And the diversion has to do with how we represent expressions. Okay? So I'll go ahead and give you an expression in arithmetics. So this is not Boolean at all. And then we'll go back to the Boolean stuff. So I'll give you an expression like, x plus y times 2. Okay, that doesn't, well, I suppose that's fine. And then times, this whole thing times x plus z, and then we take the whole thing divided by k. Okay. Don't ask me the meaning of this the expression. It has no particular meaning. It's just here as an example. So now the question is, how do I represent this as a tree? Okay. Now, how many people know what a tree is? Okay, a few people, if you have taken 430, you know what a tree is. But since 430 is not the prerequisite of this class, I cannot rely on that dependency, right? Okay, so what we'll do is we'll introduce a concept that is new to everybody. That makes it better. We'll talk about precedency, okay? Or how you can express an expression. So in this case, we're particularly interested in a prefix format, okay? So prefix format is easy. X plus y expressed as a prefix format is saying, oh, we need to do a plus. What are we adding? Oh, x and y. So this is the right-hand side is what we call a prefix notation, and then the left-hand side, or what you're familiar with, is called the infix format. So all this time, okay, throughout your entire life up to this point, okay, you're very used to infix format because that's exactly what we were taught from the very beginning. So once again, this is an example of things that are actually absurd looks normal because we have been living in it all this time. And I'm trying to tell you, the infix notation doesn't make sense. But we are so used to it, go like, yeah, what do you mean by it doesn't make sense? It makes perfect sense. No. The prefix format is better than the infix format. Okay? We're just used to infix because we have been using it for decades. Well, I'm old. You guys, maybe a decade or so. So this is how we do the conversion. So now, if I ask you, how do we convert this kind of somewhat complicated expression into a prefix format from the infix format, how do you do it? You go from the outside in. Very good. Okay, that's a great idea. So you go from the outside in, which means you think about what is the last operator for this entire expression. Division. Very good. I like that. So you say, oh, the very last or the top level operation is a division. So I'm going to use underscore to represent the two things that we need. So this is going to be the dividend, and this is going to be the divisor. Let's deal with the divisor first because it's easy in this case. What is the divisor for the division? Okay, cool. So that's easy. And what do you think is our dividend? Oh, the dividend is a big mess, isn't it? But that's okay. So we are talking about the big mess, which is this chunk here, right? So what do? Recursion. We look at the expression that I have highlighted and go like, so what is the prefix format of that infix notation, of that infix expression? So you apply the same technique again, right? Of the portion that is highlighted, what was the last thing that we do? It was the addition because multiplication has precedence over addition. So addition is the last thing that we did. Cool. All right. So now we go back here and we say, yeah, this is a complicated thing. It's an addition of something and something. Okay. So with the addition, what was the first addend? Oh, that was the easy one, x. Okay. What is the second addend? The second addend is kind of complicated. It is y times 2 times x plus z. And I'll just say that we follow exactly the same structure here. So what is the last operation of only this part of the expression? Multiplication. Very good. So now we say it's a multiplication of some kind, which means it has got two things to operate on. Okay. And this side is the multiplication of y and 2, and then this side is the addition of x and z. Now we're done. So we have just converted a infix notation to a prefix notation. Well, Are you really surprised by the prefix notation? You have been using that not all along. Yep, go ahead.
You don't really need the parentheses anymore, do you?
Yes, you do with a prefix notation.
I'm used to postfix, and
Yes, postfix does not need parentheses, and that's why it's even better.
like,
We can do that. Okay, we can do the postfix notation after this. We can do the postfix notation post prefix. Huh? Well, we'll deal with postfix later. Okay, so we got infix, and then we now get prefix. Okay, so why do you think the prefix notation is particularly helpful when we are dealing with something like that? There's no ambiguity, and the plus. Okay, with this one, what do you think it would look like? I can do one for you guys, okay, because it's kind of related to homework. So if I want to express this thing, what do you think the prefix notation looks like? It's going to be a OR operation, right? So I'm going to use OR, okay, so that's easier. So what is it ORing? G2, the conjunction of P2, G1, the conjunction of P2, P1, G0, and the conjunction of P2, P1, P0, K0. Oops, one more paren right there. Is that making any sense?
It's the last row of K3.
Sorry?
That is the last row of K3, correct?
It's this one, yeah. Okay, so when you look at this, and let's just say that we have the wires, we got all the P's and the G terms already, determined by multi-bit gates, okay? So in that case, what do you think the gates would be structured? The final gate is which gate is the final gate? The OR gate. How many inputs are going into that OR gate? Looks like 4 to me. We got 1, 2, 3, 4. Okay, so 4 things go into the OR gate. The first one is easy. It's just G2. G2 is computed by a multi-bit AND gate. Okay, so you have to take one wire out of the output of the multi-bit AND gate, and that's G2. It goes straight into the input of the OR gate. What about the second thing that goes into the OR gate? It is the output of an AND gate, right? What goes into the AND gate? G1 and P2. Okay, good. And this one, it's a little bit bigger of an AND gate. It has 3 inputs. It's got, G0, P1, P2 as inputs into this AND gate, but the output of this AND gate goes into the input of that OR gate. This one is even bigger, but nonetheless, it is one single AND gate. It has got 4 inputs. K0, P0, P1, and P2 are the inputs into this AND gate. The output of this AND gate, or the result of the conjunction, goes into one of the inputs of the OR gate. So when we get to the prefix notation, the structure is really well spelled out. And you can now turn that into a circuit diagram in Logic. Yep.
So, isn't it more complicated though in logic system because P2, all the P's, they're also going to be, they represent X's and Y's eventually.
Yeah,
so
yeah.
It's going to be more OR gates.
No, but remember, you can split a wire to go into multiple gates. Okay, you can split a single wire. In other words, you take, let's say, P2. Okay, P2 is a good example. So P2 is a single bit out of the output of the multi-bit OR gate that takes all the X and the Y bits. Okay, but once you splice that single wire out, it can go into the input of this AND gate and the input of this AND gate and the input of this AND gate. So you can take a single wire and then you split it to go into multiple gates. Is that okay? All right. So I did talk about postfix notation. Okay. So in postfix notation, let's deal with the math example first. So the the postfix notation is really kind of cool in a way because it doesn't require parentheses at all. So in the case of x plus y, in a postfix notation, it is just x, push x on the stack, push y on the stack, and then the plus operation is going to pop 2 items from the stack, perform the addition, and then push the result of the sum back on the stack. Now, if you're not familiar with pushing and popping, we can just kind of say there's a little stack of paper, right? And then in the loose sense of the word stack, there's a pile of paper. How about that? Okay, there's a pile of paper. So my tablet is not working because for some reason my laptop doesn't want to work with it. So in the case of x plus y, so what we do is this is your pile, which is empty to begin with. So you put x on this pile, you're not going to do anything. You put y on this pile, you're not going to do anything. When you see the plus, what happens is you go to this pile, remove the first 2 items on the pile, perform the addition, and then you put the result of the addition back onto the pile. Is that okay? All right. So when you look at the more complex expression, which is here. So when we look at this expression here, what are we going to do to get this done? Well, you just kind of read the whole thing. You say x, and then you go like, are we going to do anything about x? Not yet, okay? Because the addition cannot be done until that whole big mess to the right-hand side of the addition is done. Okay, so you just put it on the pile, put it on the pile at this point. And then you go like y and 2, okay? So once we have y and 2 on top of the pile of paper, we can now say, oh, we know what to do with the y and the 2. We're supposed to multiply those things. So you say multiplication, which will remove the top 2 items from the pile, perform the multiplication, and then put the product back on top of the pile. Is that okay? Are we going to do anything about the product of y and 2 at this point? No, not yet, okay? Because to use the result of this part, we have to figure out the other part first. So what you do is you say, okay, fine, we'll put x, another copy of x on the pile. We'll put z on the pile. Once x and z are on the pile, we know what to do with those. We know we have to perform an addition. So at this point, we will have 3 sheets of paper on the pile. We'll have x on the pile, we'll have y times 2 on the pile, and we'll also have x plus z on the pile. But at that point, we can perform the multiplication between the y times 2 and the x plus z. So now we say multiplication. Remove the top 2 pieces of paper from the pile and perform a multiplication. That turns out to be this part of the expression. So once we have that product, we can now perform the addition to x. So we say x plus here, right? That finishes the dividend of the division. Yes?
So in Postfix, the operator only ever operating on 2
Up to 2. Yep.
Infix, I saw that in the addition you were ask.
Correct. Yep. So now what can we do? Well, not much we can do about the dividend until we have the divisor also available, right? So now we have to put the divisor on that pile of paper, which is just k itself. And at this point, we only have 2 sheets of paper on the pile. We have the entire dividend on the pile, at the bottom of the pile. We have k on the top of that pile. Oh, that's all we need for the division, right? Done. Do we see any parentheses in the postfix notation? Nope. Do you think it's easy to parse? Super easy. And who do you think uses a postfix? I'll ask you that question. I'll pose that question in 2 different senses. One is in terms of a scientific calculator, okay? And the second one is in terms of a programming language. Yep.
I know I've used it in C++,
Okay.
Can I guess?
Yep. Go ahead.
Fortran idea.
Fortran doesn't use postfix as far as I know, so I could be wrong about that. But in terms of calculators, all the HP calculators use that. It's called reverse Polish notation, or RPN. So if you look it up, these are pretty archaic, calculators from like 2 or 3 decades ago. I actually got the, actually they kept RPN until very recently. Yep.
I just thought about it. This would be perfect because you're only handling two objects. This would be perfect for assembly.
Yes. It's perfect for translating C or high level code into operations that are very simple that can only do like two things at a time. Okay. But these calculators, can handle RPN, but they can also use the current, the infix notation. So most people say, oh, this is progress. I mean, HP finally has joined the bandwagon of infix notation. I look at this as a step back. I think more calculators should use RPN and not the other way around. Yes.
I was I used to be a surveyor. We used reverse Polish notation.
Sorry.
As a surveyor, I used to use reverse Polish.
Yep. Yeah, HP calculators were very, very popular in the 80s and even in the early 90s. So if you're an engineer, you have an HP calculator. If you're in the financial world, you have an HP calculator. And they all use RPN. So if you have an engineer, like an uncle or parent, you can ask them and go, what is RPN? Okay, and just block off half an hour so they can finish the explanation. Because anyone who uses RPN is passionate about it because it is so, it's weird because we are so used to infix, but once you get used to it, it actually makes sense.
It's good for calling out computations to whatever.
Right.
person.
And it's easy to parse. So it's easy to make a parser out of it. So for those of you who want to play with this but decide I don't want to pay extra money for something like that, there's an actual RealCalc as an Android app. You can download it as a free app. There's also a paid version, but even the free version can do RPN. And this is my calculator app. Because it can do everything that I needed to do. But it can also do infix notation. So if you go like, oh man, this is too much trouble, you can go back to use the infix notation. It can do base conversion and a whole bunch of other stuff. I just like it. Okay, so that's kind of a digression from the main topic here, but it does illustrate the importance of infix because that's what we are used to. Prefix, which you already have exposure to because that's how we call subroutines. Okay, let me go back to that one and see if we can make it look like subroutine calls. Not this one, this one. There we go. Okay, so how do we turn this into a representation of function calls? So that's pretty easy. Imagine that we have a div subroutine that takes two parameters, right? So the two parameters are here. And then imagine that we have a add subroutine that also takes two parameters. So that would be these two, I think. And then we have a comma to separate the parameters. This is multiplication. Okay, that takes two parameters, like that. But you can see how I can easily convert a prefix notation into subroutine calls. Okay, so once again here we have a mult call, and then we just need to separate the parameters with a comma. And then here we have a add call, and we separate x and y with a comma. Does that look familiar? Just function calls. So the prefix notation is closely related to function calls of functions that return a value. So the return value of one function can serve as the argument to another function call. But it's the same thing. You already know this stuff already from cisp360, even 300. Is that okay? All right. All right. So getting back to what we were talking about before. So how do we generate all these P and the G terms? Remember, we can use multi-bit gates, right? Okay. So what I'm gonna do is I'll throw you guys a big bone. Look at this as a bone of a dinosaur. It's big.
Kind of dinosaur.
Huh?
Kind of dinosaur.
That's right. They do have tiny little dinosaurs, right? How about T-Rex? All right. So we'll go ahead and do I have it here? Yep, I do. Okay, good. So I'm going to show you two examples, okay? Two ways of doing exactly the same thing. Then it'll be pretty clear to you, how to use a multi-bit gate so that you can simplify your design, go like, oh, okay, that's easy. All right, so the first thing we're going to do is to chop bits off into individual parts, going into individual gates, and then combine everything back into one. Okay, so this is absolutely the long way of doing things. So this is a 2-bit input, okay? This is going to be another 2-bit input, and this is going to be a 2-bit output. Okay? So let's just say that I want the output to be the conjunction of the inputs. So bit 0 of the output is the conjunction of bit 0s of the input. Bit 1 of the output is the conjunction of bit 1s of the input. But let's just say that we have no understanding of multi-bit gates at all. Okay? So we have to do it the long way. So we'll go ahead and do it the long way, which means we have to use splitters, because that's the only way we can split a multi-bit input pin into the individual bits. Okay? So we split this guy, duplicate it over here, split the other one, right? So now we need AND gates. How many AND gates do we need if we do not use multi-bit AND gates? We'll need 2 AND gates, right? We need one AND gate to take care of bit 0. We need another AND gate to take care of bit 1. So now we're going to go pull 2 AND gates. And by the way, you can pull AND gates here too. So we can pull an AND gate. It's got too many inputs. This is the other thing that we will learn over time is you do not want to leave input pins unconnected. Because any pin that is unconnected in the physical world means the value is not specified. It is neither a 0 nor a 1. Sometimes it's a 1, sometimes it's a 0. It depends on whether your phone is next to your computer, someone turns on the microwave or not, the phase of the moon, is there a solar flare, and so on and so forth. So do you want your computer to behave differently depending on all those factors and some more? Probably not. So don't leave any input pins unconnected. So that means you want the number of input pins to match exactly the number of pins that you need. In this case, I just need 2. So we'll duplicate it because we need 2 of these guys. Okay, so we have 2 of those things. And then we'll use the top one to take care of bit 0. So bit 0 of the top input pins goes into one of the pins here. Bit 0 of the bottom input pin goes to the other input here. And then the output of this, we'll do something with it later. Bit 1 of the top input pin goes to one of the inputs of the other AND gate. And then bit 1 of the bottom input pin goes to the other input of the bottom gate. Okay? I don't see any orange colors, so the bit compatibility is fine up to this point. So now my problem is I have the result of bit 0 from the top AND gate. We have the result of bit 1 from the bottom AND gate. So we got 2 wires coming out. But I have to combine those in order to feed it into a multi-bit output pin. Okay? So I need the reverse of a splitter. Okay? And by the way, the reverse of a splitter is just a splitter. There's no special name for that, even though functionally it is a merger, but it's not called a merger. It's facing in the wrong direction. I can make it work, it just looks really ugly. So it's good to kind of flip it horizontally. So you can change the facing from east to west. So now it is, it looks like this. The output of this can go straight into the 2-bit output pin, and then bit 0 of the result goes into bit 0 of the splitter, and then bit 1 of the result goes into bit 1 of the splitter. And I think we got it done. You can see the result is 0, 0. So, okay, let me illustrate how it works. So if I change this to a 1, and this one to a 1, and this one to a 0, that really shows, how it works. Because bit 0 of the output pin is now the conjunction of 0 and 1. That makes sense. 0 and 1 is 0. Bit 1 of the output is the conjunction of 1 and 1. That works, right? In other words, yes, you can make it work like this. Remember, your X and Y's are multi-bit input pins. Okay? That works. So let me show you the other way to do this. Okay, we'll move these guys over so that I have room to tap the output of these things. But I would need another output pin. Okay, so we'll put the other output pin here. And this time I'm going to go, well, I do understand how a multi-bit gate works. So I'm going to make use of that. All right, so we'll duplicate one of these gates here. A multi-bit gate does not look any different compared to a single bit gate. I can change the data bits from 1 to 2 now. Now, then I can just connect this guy over here. It's error because it has no input, but that's fine. We can fix that. One of the inputs of this multi-bit AND gate comes from the top input pin, and then the other one comes from the bottom input pin. I'm done. So, unless you really wish to punish yourselves, okay, which I'm not going to stop, you can do it the top way, the complicated way, split, make lots and lots of individual gates, merge all of those things back in. Or you can do it the bottom way. We just go like, yep, we know how a multi-bit gate works. Pretty easy. So is that illustrating how to use a multi-bit gate? Yeah? How does this relate to the computation of the P and the G terms? Yep. Yep, if this is X and this is Y, what term are we computing now? X and Y, so is it the P or the G's? It's the G's, exactly. So when you look at this output wire here, it is a multi-bit wire, okay? But it represents G0, G1. They're both combined here. When you look at the individual output, which is here, this is G0, this is G1. Then you go like, well, if we have G0 and G1 bundled into this wire, how do we split it up? Because sometimes we just need G0, other times we just need G1. Get a splitter. Okay? Now, splitters are funny. They're actually very flexible. So let me just duplicate the splitter so I can illustrate what you can do with splitters, in addition to what you have done already on Tuesday. So you can have a splitter that only has one output. In other words, you can make it like this. Oops. Okay. So you can make it look better. Okay, so in this case, I changed the fan out to just one. Okay, and it only outputs bit 0. So this splitter at this point is coming from a 2-bit wire. It ignores bit 1 and then the only way out is just bit 0. In other words, you can make a splitter not to give you all the bits from the bundle and just give you the one bit that you need from the entire bundle. Okay, that's an option. Or alternatively, if you do need all the wires, then you can just say, okay, I'm going to have fan out of 2, and I connect bit 0 to a bunch of places, and I can connect bit 1 to a whole bunch of places. Is that okay? Any other questions? All right, if there are no questions, let's zoom out again, and I'll basically give you some questions that can help you do the lab activity for today. If this diagram, ignoring the complicated part, is computing the G terms, how do I make it compute the P terms? Yep, exactly. Do an OR gate, right? So can I do an OR gate in parallel to this AND gate? Absolutely. So the AND gate will give you all the G terms, the OR gate will give you all the P terms, right? And then you can use those P and G terms to compute the various K terms, the carry terms. Is that okay? Now the carry terms, unfortunately, cannot really benefit from multi-bit gates because they're all different. So K1, the equation of K1 doesn't look like the equation of K2, which does not look like the equation of K3. So you can't really utilize this method. So the K terms are kind of individual, and each one has its own subcircuit to get it done. So are we good so far? All right. So with this out of the way, which this really should help with your lab today. And by the way, today's lab, I give you until the end of today to turn it in, to finish the quiz, because it might take a little bit longer than the lab time, so you have more time to finish it. All right, so getting back to here. So once we know what K2 looks like, what K3 looks like there's a certain pattern to it. So once you generalize the pattern, we get to this form here. So what exactly is that form? We talked about this a little bit. So we'll start with the easy one. We'll start with this side here, K0, and then the big conjunction thing, and then a whole bunch of PI terms. Look at that as a loop. Look at this as a loop of for I equals to 0, I is less than or equal to n, and then the loop is saying, okay, we'll do a conjunction of all the PI terms. Okay, instead of just talking about it, I'll give you the visual of that code. Okay, so where's my, this one. Drag it down just a little bit. Okay. All right, so we're going to do the second term first. So the second term basically has to start with a local variable bool. Okay, so we'll say this is, we just give it a particular name. I'm just thinking about what name to give it. I'll call it T1. Okay. And T1 is initialized to true. Okay. This is pseudo C, it doesn't compile, but it illustrates the concept. So now we say for I equals to 0, I is less than or equal to n plus plus I. And then inside the loop here, all we're going to do is to say T1 is T1 and P bracket I. So P subscript I, means we are accessing bit I of all the P terms. So in the C code, I'm using P bracket I to mean exactly the same thing. So are there any questions about this part, implementing this kind of conjunction thing? Are we good so far? Yes? Okay. All right. So now that we have that term, let's see what we can do to deal with this kind of horrible looking thing where we have a conjunction loop inside a disjunction loop. Well, it's a double loop thing. So with this double loop thing, we have another Boolean term. Let's call it T2. And then we have a loop for I equals to 0. We stay in loop as long as I is less than or equal to n plus I. Okay. And all we're going to do here is to have another local variable bool. We call this T2. Oh, by the way, T3. But this one needs to be initialized. With an OR, T2 is initialized to false. So inside the loop, we have a local variable term T3, and T3 is initialized to true. And then we are going to take care of the embedded AND loop here. So we have another loop. So this time we have for j equals to I plus 1. J is less than or equal to n plus j. And then we get back here. And then for each loop, or for each iteration of the inner loop, we say T3 is T3 and P of j. Yep.
Why was T2 initialized to false?
Why is T2 initialized to false? Because, well, you will see later, because we have not utilized T2 just yet. This is using T3. Okay? So when we get out of the inner loop, then we have to compute, we have to deal with T2. So now we say T2 is T2 or, and in parentheses, G bracket I and T3, and T3 is the result of the inner loop. Okay, and that's it. When we're done with both of these loops, we just have to do a disjunction. So the result, K bracket n plus 1, is then T2, which is the result of this portion of the expression, and then do an OR with K0 and T1, because T1 we computed like way from the beginning, which is this part of the equation. And let me see if I can Can I resize? There we go. There we go. So I think that shows the entire algorithm. So this entire algorithm in the text editor is reflecting the calculation of the equation. Yep.
The bottom line between T2 and the parentheses.
Uh-huh.
That you said that's an OR. You're using OR as the two lines up above.
Are you referring to this OR?
Yes.
So this OR is implementing this OR.
Okay.
Because the outer loop is an OR loop. The inner loop is an AND loop.
Okay.
So the result of the AND loop is first conjunction with GI. That's why we have this. And then that result is cumulative with the OR loop. So T2 is keeping track of the result of the OR loop overall. Is that okay? Question?
But on the bottom line, there's a plus sign there. Is that what you meant to do?
Oh, that's an OR. Yep. Okay. Yep. That was my bad.
That's all in that was.
Oh, okay. I see.
consistency of-
Yes. So this is supposed to be, oops, wrong place. Undo. Turn this one back into OR. There we go. Thank you. Yep. Say that one more time.
If you stick to the like summing notation
Uh-huh.
for the disjunction, like right there
Did I forget about that somewhere?
in the formula, you have a plus sign, right?
In the formula, I have a plus sign. Yeah, that's an OR. That's just a regular, that's a logical OR.
So could you change that disjunction? Like there's the sum I equals 1. If you're sticking with that notation.
Using sigma. Yeah, I suppose. But I don't want to use sigma because sigma does indicate that we are just doing regular addition. So that's why I use the V symbol for disjunction and then the TP for conjunction.
But they are like if we think of the notation, they're just pluses.
Right. Yep. hmm But this does spell out, what the expression is doing. So are there any questions about the loop itself? Yep.
Which one is for T2?
Huh?
Which one is for T2?
Which one is for T2?
Yeah, for the bottom one, the bottom the
I don't understand what the question was asking.
the last formula. So that's what Kn.
Okay, let me include line number so we can easily designate which line we are talking. Wait, hold on. Okay, which line are we talking about?
That line. The 50.
Line which?
Line 54.
Thank you. Okay, so on line 54, what about line 54?
T2.
Yeah, this T2.
Yeah, T2. Which one is for the T2 on the formula? The Kn.
T2 is this entire thing.
This T2, right? The first.
T2 keeps track of the result of this entire thing. So, okay, since this will be recorded. So T2 is responsible for this entire thing. And then T1 is this part, just that part, okay? And then T3 is tracking only this part. But because this is an inner loop, so that's why T3 is a local variable inside the loop, because it needs to be reinitialized every single time. Well, it can be outside of the loop in terms of declaration, but it has to be reinitialized every iteration before the inner loop. Is that okay or not? This is, I'm just explaining the notation, the more or less mathematical notation, using a procedural way of saying, okay, if you were to do this by using a computer, using a program, this is how you do it. Yep.
Can you repeat again what's the differences between having the V and then TP again?
So the V is OR, and then the TP, or the inverted V, is AND. But since we're ANDing over a whole bunch of terms, so instead of spelling out the terms, I'm just using the same notation as a sigma in summation, in arithmetics. So this way I just need to specify the begin index, the end index, and then we just do the AND or the OR operation over that entire range. Is that okay or not? And by the way, this is new for this semester. In the previous semester, I never explained these using pseudo C code, but this time I'm just going to give you the pseudo C code so that you can track down the C code and then use that to help understand what the expression is trying to express. Are we okay so far? Sorry? Pseudocode helps. Very good. I'm also doing the same thing in 440. I'm using pseudocode to help explain some of the concepts in that class. So are we good so far with addition using carry look ahead? Good? All right. So we got a few things that we can do. We can go back and try to implement an adder, but using carry ripple, the carry ripple method, which makes it very kind of slow, okay? Or we can move ahead and start to talk about subtraction. So which way do you guys want to do? Do we want to start with subtraction, or do we want to look at carry ripple adders? Carry ripple adders? Okay, let's do that. Okay. So to illustrate it, I can just use a Logisim. So this is also going to be, this is also a good example of how to use Logisim and do it in a kind of structured way. Okay. So we'll start with a particular design to do what we call a half adder. So we'll have two input pins, X and Y, and these are single bit. We'll have two output pins. This is going to be the result, and this is going to be the carry. So I'll name these things accordingly, so this way it is somewhat self-documenting. So this is X, this is Y, and this is, well, we'll use R as the top one, which is the result after an addition, and this is going to be C or K, which is the carry of a particular addition. Is that okay? So now we want to specify the gates to do it. The carry is easy. We just need a conjunction gate with two inputs. Oops. And we can make it look a little bit smaller like that. And that's going to be the carry. So the carry is nothing more than bit X and bit Y. So here's X, and oops, and here's Y. We're done with the carry. The result is a little bit more complicated. Remember the X not Y plus not XY? But there's a gate to do that with one single gate. It's called the exclusive OR gate. And you are allowed to use exclusive OR in your homework assignment. So keep that in mind. So you go to gates, and you look up exclusive OR, which is spelled as XOR. So you pull that out, do the same thing, make it smaller and only two inputs. Okay, like so. And that's going to be responsible for the R bit. There we go. And this is what I mean by tapping the same wire so that it can serve as input to multiple gates. So now we are done with what we call a half adder. Let's give it a try. 0 plus 0 has a result of 0 and a carry of 0. Sounds good? 1 plus 0 has a result of 1 and a carry of 0. Sounds good? 0 plus 1, same thing, has a result of 1 and a carry of 0. Looks good? And 1 plus 1 has a result of 0 but a carry of 1. All sounds good to me, right? Now, this is really particularly useful. So what I'm doing now is I'm turning this into a overall circuit. So let me see how we can do that. So this is our main circuit. So every time you have a circuit, which is referring to this thing here, so every time you have a circuit, you can change the name of that circuit. So I'm going to change this to a half adder. Half adder. And then we'll go ahead and edit the appearance. So here's the default appearance. Now with the default appearance, the input bits are not really particularly concerning unless we are dealing with a subtractor, because with a subtraction, you do not have the commutative property. But just to be safe, I'm just going to label these things accordingly. And then we'll just move these things to the right place. So we got X, Y, the result of adding X and Y, and then the carry of adding X and Y. So now we have a component which I can use in other circuits. Is that okay? So next, I'm going to make a full adder. I mean, just because I call this a half adder is already telling you or hinting that there might be a full adder. Does that make sense? Because otherwise, I wouldn't call this a half adder. So I go to project and I say, let's add a new circuit. The name of the new circuit is a full adder. So in a full adder, as you probably expect, without even knowing what a full adder is, how many half adders do you think is in a full adder? Very good. No need to send anyone back to remedial math. So we pull 2 of these from our library. In other words, anything that you make as a circuit and you give it an appearance, now it becomes an available component to make even larger components, which is great. It's basically the concept of a subroutine. It is encapsulation. Okay? So now we have 2 of these things. All right, so let's go ahead and give it some pins. So here's X, Y, and guess what? We have 1 more input pin this time. It's called carry in. And then we have 3 outputs. 2 outputs, excuse me. We've only got 2 outputs. All right, so we'll label these things once again. This is my X, Y, and this is what we call the carry in. So I use C in for carry in, and we'll call this one our carry out. And this is going to be the actual sum bit, so we'll use S to represent it. In fact, yeah, that's fine. All right. So we'll feed X and Y directly into X and Y of the first half adder, like so. So this R here is basically our Q term. Does that make any sense? Do you still remember what the Q term is? Okay. So that's our Q term. So I'm going to bring out a wire here, and I'll just kind of annotate that wire and say this is our Q. Oh, by the way, there's a really cool feature to annotate stuff and make the circuit kind of self-documenting. It's the concept of a tunnel. Okay, so I'm going to give you a tunnel here. A tunnel is kind of like a label that you can attach to a wire. And the whole idea is you have to label a tunnel. So in this case, I labeled the tunnel Q because it is actually our Q term. So now with this wire labeled as Q, I can now add additional tunnels elsewhere in the entire circuit. As long as those tunnels are also called Q, they are actually connected. Every tunnel of exactly the same label are logically connected. So that makes it easy to draw circuits that are complicated without a lot of wires flying around. Because now we can use tunnels to say that, oh, this particular wire is here, but I also want to use it down here. Well, use a tunnel. Otherwise, you need an actual wire to go across everything else, which can be confusing. But once you use a tunnel, not only can you reduce the number of wires, but it's also self-documenting. Okay. So just to illustrate how it's used, okay, we can duplicate this Q. Come on, there we go. And this Q will serve as the input to the second half adder. So I need to change the facing, just so that it looks nice. Okay, there we go. And what do you think goes to Y? Okay, so this is the process of elimination. Even if you know nothing about binary addition or the previous things that we have talked about, if I tell you that we have all the components already, it's just a matter of wiring the components, especially from the input perspective, there's only one place it can connect to, right? Because all the inputs are already occupied except for one. And then we have one input pin that is not connected to anything, right? So if the circuit doesn't have extra components and is not erroneous, there's only one way to connect to Y of the second half adder. It has to be coming from carry in. So carry in is basically the carry from the previous column when we look at it from the perspective of the spreadsheet. There we go. All right. Cool. And what do you think this R is going to go to? Now, sum, exactly. So this is our sum already, easy peasy. Now we have a bigger problem, because the bigger problem that we have now is we have 2 carry outputs, this pin and this pin, and we only have 1 single carry output of the entire circuit. How are we going to do this? Well, we don't necessarily need a tunnel. The tunnel is only good for making things look better, but it doesn't really change the logic. Yep. We need an OR, exactly. So the first carry, the carry of the top, is the carry of adding the input bits, x and y. That gives you the Q term. What do you do with the Q term? You have to add the Q term to the carry coming from the previous column, the column that is less significant compared to this column. That's why we have two half adders. So that can give you another chance of getting a carry. But a single OR is capable of doing what we need to do because we know only one of these two can be a 1. Up to 1 can be a 1. They cannot both be 1s. So that means a single disjunction is going to get the trick done. So now we put this, change the size of this thing so it's smaller. And yeah, we can put it here. I'm not particularly good at making things look good, but it would be functional. There we go. Now we have a full adder. So let's try this out. So we say, what is 1 plus 1, and then with no carry coming in from the previous. Well, the result is a 0. The sum bit is a 0, and we have a carry to the next column. Okay. What if they're all 1s? Well, in that case, we have a result of 1 and also a carry to the next column. Are we doing okay so far with this? All right. So now with a full adder, it is one single column of the addition representation. So now with a full adder, we can now say, can we make a 3 by 3 bit adder? Sure we can. So we add another circuit again. We say this is a 3 by 3 adder. And then this time we use full adders. So a full adder looks like this, and unfortunately I did not label the pins. But we kind of know this is X, Y, and carry in. This is sum, and this is C out. I mean, if you hover over, it will still give you the label, but otherwise it can be confusing. And the way I'm going to do this is I'm going to change the phasing. So it's going to face south like that. And then I will duplicate this 3 times. Oops. Yep.
So now that you created the adders, how did you get them in the pane on the left? It just automatically appear there, or?
Ask the question again, sorry.
You created the half adders, right?
Yep.
And it looks like they're showing up in the library pane on the left there.
It's here.
Oh,
So the half adder is here. The full adder is here.
get it in there.
How?
Yeah, how did you?
As soon as you add a circuit, it gets added to there.
Okay.
Yep. All right, so we are almost done. Okay, we are running a little short on time, but I'm going to show you. Yeah, this is going to take a little bit longer than 2 minutes. So basically, we have x0 going here, x1 going here, x2 going here, y0 goes here, y1 goes here, y2 goes here. The sums would go to the individual bits of the sum. This goes to S0, S1, and S2. The carry bits are the fun ones because this carry out goes into this carry in, this carry out goes to this carry in, this carry out is just going to hang out on its own as an individual output pin. Then it becomes a 3 by 3 bit adder. Now, yep, go ahead.
So a 3 by 3 bit adder will always have 4 bits of output?
Yes, so there are 3 bits of the sum plus the overall carry. So this is the part that I really need to emphasize is the dependency between the full adders. So you can see how the last full adder depends on the second full adder. The second full adder depends on the first full adder. This is why it's called a carry ripple mechanism, because the carry is just quote unquote rippling through the full adders in a sequential or in a linear fashion, which is not what we want. right? We want things to be done quickly. And that's why we want to use the carry look ahead mechanism, where every single carry bit only needs 3 levels of gate logic to compute. Once we have the carry bits, once we have the Q bits, the sum bits are easy to compute. I'll give you a clue. Use a multi-bit exclusive OR gate. Because once you have all the carry bits, combine them into one big bundle. Once you have all the Q bits, which should start as a bundle to begin with, take those 2 bundles, feed those into a 2-input multi-bit exclusive OR gate. The output of that exclusive OR gate is going to be your sum bits. I can give you that bone because that's not the complexity of the carry look ahead mechanism. The complexity of a carry look ahead mechanism has to do with how do you compute K1, K2, and K3. And that part is going to take some time to kind of figure out how to come up with a logic design. All right? Okay, so I'm going to stop the recorder now, and we'll get out of the classroom so the next class can come in. And then the lab has a